Assalamualaikum and good day everyone. Let's continue with part 2, design consideration for structure timber beam. Beams are the most commonly used structural element. For example, floor joists, rafter and etc. This is the picture showing the floor joist made of timber. Okay. It's spaced at the specific distance, and on top of this joist we put slab or flooring. This is the cross-section for the beam with the concrete floor. If you see, timber beam can made of solid timber or gululan timber. And this is the picture of rafter for roofing. Size of timber may be governed by the requirement of elastic section modulus, which is Z. This is to limit the bending stress and to ensure that neither torsional buckling of the compression flange nor fracture flange induce failure. Second is cross-section. This is to ensure that the vertical or horizontal shear stress do not induce failure. Then we have second moment of area or I. This is to limit the deflection induced by bending or shear action to acceptable limit. We have two types of sawn timber. First is rough sawn or full sawn. This timber is not dressed or surfaced, but it's sawn, aged and trimmed. The dimension is oversized so that it's allowed for shrinkage and before fully seasoned. We can refer to table B3A and B3B Malaysian standard to see the properties of this sawn timber. This is the picture of the sawn timber. Next, we have a dress-on surface timber. So this is the picture. This timber has been dressed by planing for smooth surface and uniform dimension. The dimension is measured at dry. So for this dress timber, we can refer to table B4. Table B3A, B3B, B4 can be obtained from Malaysian Standard 544 Part 2. Here I screenshot one of the table, which is table B3B. This is the geometrical property of sawn timber at 19% moisture content. Let's look what we have in this table. We have the nominal size, this is size, and also the minimum size. This is the B times H, okay, which is the cross section of the timber. We have the area, and then we have the second moment area, IXX and IYY. The section modulus, which is Z, both at X and Y direction. And lastly, the radius of creation. We can just use this table for our detailed cross-section properties of our timber sizing. Timber is anisotropic material where the stress depends on the grain direction. We have to understand how to read and write the timber stress according to the type of force, significance, and geometry. For example, here, stress, M, A, and one symbol here like inverted T. We read this as applied bending stress perpendicular to the grain. First is the stress, okay, and we followed by the type of force. We have M here stand for bending. So we have other such as C for compression and T for tension. It followed by the significant where A is stand for applied. We have other also like ADM, which stand for permissible. Lastly, it followed by the geometry. We have parallel and perpendicular to grain. As in this example, this inverted T is perpendicular to the crane. The grade stress is defined as a stress which can safely be permanently sustained by material of a specific sizing at a particular strength class or species. We can refer to Table 1, 2 or 4 in Malaysian Standard Part 2 to see the material properties of this strength class. We have three grades of stress. We have select, standard and common. Let's look at one example of material properties table we get from Malaysian Standard 544. I take table 1, which is wet grade stresses of timber with moisture content more than 19%. We all know that properties of timber different according to grain direction. So first we have the type of timber, and these are all the value for the material properties. We have bending parallel to grain, tension and compression parallel to grain, compression perpendicular to grain, as well as shear parallel to grain. And lastly, we have the modulus of elasticity. For stress properties, we have three grades. SEL stands for select, STD is for standard, and COM is for common. All these grades has its own stress value. The highest value is for select, and the lower value is for common grade. I advise you to refer to Malaysian Standard to get familiar with the properties table. Under design consideration, we have two types of stresses which we need to compare. Okay, first is the permissible stress. This is governed by the particular condition or service and loading. In timber structure design, list of check for permissible stress are flexural strength, shear strength, bearing strength, lateral stability, and deflection. The second stress is the applied stress. This is determined by elastic analysis, where we assume the structure in elastic behavior. Then we have to refer to the elastic theory. So in the elastic theory, the assumption is that material is homogeneous, where it have same physical properties. The material is isotropic, where the elastic properties same in all direction, and then lastly it obeys Hooke's law. When we design, we have to make sure that our applied stress less than permissible stress. Applied stress is determined using elastic theory. Permissible stress is notated by ADM. And it is determined by grade stress times with modification factors. In order to take account for uncertainty in the design, there are many different adjustment of strength using modification factor. Commonly used factors are duration of loading, K1, load sharing system, K2, bearing stress, K3, shear at notch end, K4, form factor, K5, and depth factor, K6. So in the next slide, we will be looking at all these factors and how it affects our design strength. Time has a great influence on mechanical properties of timber. When subjected to loading, the strength properties is reduced, and the longer the duration, the greater reduction can be. So the first design consideration we have to take care is the modification factor of K1, duration of loading. By referring to Table 5 Malaysian Standard, there are 4 terms for duration of loading. For example, we have the long term, given K value is 1. For medium term, the K value is 1.5. to 5, and so on. The second modification factor is load sharing system, K2. If you see in this figure, where load is distributed on equally spaced member like this flow joist, the distribution system enables load sharing to take place between members, and this will allow the member strength property to be increased in value. If the number of elements is 4, like here 1, 2, 3, 4, or more, the distance between elements is less than 610 or equal to 610, it has adequate provision for the lateral distribution load. So the K2 will be equal to 1.1. So if we want to use K2 1.1, we have to use E min to calculate deflection and displacement. However, if there is no load sharing, the K2 will be 1, and we use the E minimum to calculate deflection and displacement. The third modification factor is bearing stress, K3. At any bearing on the side of timber, the permissible stress in compression perpendicular to the grain is dependent on the length and position of the bearing. For bearing less than 150 mm and located 75 mm or more from end of the member, K3 should be determined according to table 6. Bearing stress of any length and bearing located at any place and have length more than 150 mm, the K3 is equal to 1. This is the table 6 to obtain modification factor K3 for bearing stress. So the first row is the length of bearing, okay, and the second row is the value of K3. So as in this example, the bearing is 150 mm, so the value of K3 is equal to 1. The fourth modification factor is shear at notch end, K4. At the end of the flexural member, the stress concentration occurs at the notch area. So that's why we need to take account of this into design. We have two types of notch. First is underside notch, and secondly the top notch. You can see the difference where the notch is located or placed. So for underside notch, we use the K4 equal to HE divided by H, where H is the total height of the beam and HE is the height that's subjected to notch. For the top notch, we have two conditions. If A is less than HE, so this is the A, the distance A. So A less than HE, we use this formula for K4. Whereas for if A more than HE, K4 is equal to 1. The fifth modification factor is form factor. So this is related with this cross-section of the timber member. For the rectangular cross-section, we use K5 as 1. Other shape of cross-section, we use K5 1.18 for solid circular and 1.41 for solid square section loaded on a diagonal. The sixth modification factor is depth factor. The grade bending stress given in table 1, 2, and 4 apply to material having a depth up to 300 mm. So if the depth more than 300 mm, we should multiply by the depth modification factor 0.81 h to the power of 2 plus 92,300 divided by h to the power of 2 plus 56,800 for solid and glue laminated beam. Another design consideration we should look after is the lateral stability. Lateral instability may affect members subjected to bending when the compression zone of the member is not fully restrained against lateral movement. So if you see in this figure, this is the types of the lateral bracing or restraint that we can provide along the beam length to avoid the lateral movement. We should calculate the depth to breadth ratio of solid and laminated member of rectangular section, and we compare with the guideline given in table 7 Malaysian standard. This is the degree of lateral support, and here are all the maximum value for the depth to breadth ratio. We have to make sure that the calculated depth to breadth ratio less than the value given in this table.